Cool. Um, well, welcome everybody to our first Lunch and Learn. Today's topic is going to be a little bit different. The title is about trying to just explain what a day is in astronomical terms, which hopefully I will demonstrate is not as hopefully straightforward as you thought. If you're familiar with mean solar days and apparent solar days and sidereal days and analemmas and the obliquity, the ecliptic, and eccentricity, then this should all be familiar to you. But otherwise, here we go. So one of the kind of things that inspired this is there's a lot about these topics online, some of which I'll show you here, but they're actually surprisingly difficult to get a grasp of, mostly because they're very difficult to visualize. So I basically want to, there's this program here called Starry Night Pro, which is an incredibly, surprisingly sophisticated piece of astronomy simulation software. And it actually makes it kind of cool to demonstrate some of these effects. This software actually can control telescopes and all sorts of other things, but here we'll use it to visualize what are otherwise some pretty subtle concepts that frankly took people quite a while to figure out. And by quite a while, I mean the Greeks knew about this, so which is really impressive when you'll see some of this. So first of all, just to get us started, I'm going to just show you, right now this software is set to March 20th, 2018, which is the vernal equinox, or the spring equinox, like ver as in green, so like the vernal equinox. Also, it's about the latitude of New York, about where we are now. So this is a pretty accurate simulation of where the sun is at any given time. And now you can play with time here, so here so we'll see the whole expanse of a day. And you can plot the motion of the stars and everything like that, and it will simulate day and night and the moon and where everything else is too. So this is sort of the basic time-lapse view you'd encounter, but we're going to do sort of demonstrate a couple more things here too. So the first thing I'm going to do to sort of start us off here is I'm going to center and follow the sun here. And then we're going to also continue to follow this. But one nice thing about this software is that, well, you can turn off the horizon, and I can also turn off daylight, so we can really see the sun go below the horizon as well. And what you'll see right here, this green line is basically just where the horizon is to keep us track of everything. So at any time of day, I can look at the entire celestial sphere. The first thing I'm going to put up in here is sort of our celestial guides, if you will. And this here is, you can see you see that red dome superimposed on top of the sky here a little bit? It's a little faint. This is sort of the first concept I want to introduce here that's sort of as a set of reference frames to kind of keep track of where everything is going here. So let me turn off this local path quickly. So this is called the celestial sphere, and it's basically what happens if you project a grid on top of the stars. It's kind of based on the assumption that the stars themselves are extremely fixed points in the sky. That's not truly true. There's apparent motion, proper motion rather, that the software actually properly tracks, which is nuts. But right now, for example, Polaris here is at the north celestial pole, as you would expect. And everything's a little bit off kilter here because, well, we're at New York's latitude. But to make this a little bit easier, we're going to move ourselves to the North Pole, actually. I'm going to reset the time here as well. So I'm going to move myself to the North Pole because I think that'll help keep everything in reference to where we are. Cool. So here we are at the North Pole. The reason this is kind of a useful place to be is because it's a little bit easier to visualize where you are in the sky at any given time. It's as if you're sitting on top of the planet Earth and looking down. So with the vernal equinox, there's no the tilt of the Earth relative to the sun doesn't matter. So you see the sun sitting directly here on the horizon. And actually, from the North Pole, everything kind of just spins around you. You can kind of see that you're watching the Earth spin underneath the stars right here. trying to like move this in a little bit slowly because as you'll see, keeping track of these reference frames gets increasingly more challenging as we go along. So we'll wait for the sun to come all the way back around, and that is what a day looks like at the North Pole right around the vernal equinox. And you can see here Polaris is at the top there, so this is sort of aligned with the Earth. One thing we're going to do here is try and talk about one sort of difference of this like type of day. So one thing we're going to do is I'm going to try and paint a line here. Paint this meridian line. And we're basically, so here's a line that's sort of relative to the horizon, right? As if you like looked at like a mountain or something like situated at the top here. And the first thing I want to demonstrate is what happens when the day advances by 24 hours and introduce this concept of a sidereal day. Sidereal's etymology is from stars or stellar day. So when the day comes right back to where it started again. So one thing I'm going to do is I'm going to find a reference star here and advance the time to sort of use this. One thing we can use is, let's actually use this star right here. So this is, I'm going to zoom in a little bit here too. This is the constellation Orion. And you can see on the top left here is the star Betelgeuse. If I click that, yeah. So there's Betelgeuse. And we're at like 6:03 p.m. And basically, what I'm going to do is I'm going to advance by 24 hours, or 86,400 SI seconds. And if you do that, I'll do this like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. So interesting enough, Betelgeuse did not get back to our like same line here. It's actually about 2 minutes, about 4 minutes fast, specifically 4 minutes and 4 seconds. And the reason why that is that the Earth, the way that we count a day is not when the stars come back to the same spot. It's when the sun comes back to the same spot. And there's one important factor about the solar system that's useful to know when thinking about that, and that's the fact that the Earth is also going around the sun as well. So what you just saw here, going Betelgeuse back to Betelgeuse here, is the Earth spinning 360 degrees. But in reality, it needs to spin 360 degrees. It actually needs to spin 360 degrees and then a little bit more to catch up with the sun, because we have gone around the sun just a little bit in that day, specifically about a degree, because there's 360 degrees and 365 days, so we've advanced about a degree around the sun. That subtlety there is actually pretty important because it means that, as we'll see later, the amount of time in a day, the amount of time it takes for the sun to get back to where it is, it depends on how fast the Earth is going around the sun. Another way to visualize that is if you look at the sort of idea of a sidereal day, right? This is basically an exaggerated way to show that as you go around the Earth, you need to like rotate just a little bit extra to get back to where the sun was in the original spot. So that is, that'll come up later, once again, because this idea of a day matters about how fast you're moving around the sun. So that so that's how we've sort of seen that there's this like reference frame of the stars here, and we sort of assume that there's this perfectly fixed place in the heavens beyond us. The next thing I wanted to show you was a different reference frame here, and that's known as the ecliptic. So if I turn, I'm going to turn off this like gray meridian here. I'm going to turn on the ecliptic, this grid here. So hopefully you can see that there is another like green I know this is probably a little bit dim on the projector here, but there's another green grid that's superimposed here on top of this red grid. So the red grid is what happens if you extend the Earth and the North Pole and the South Pole out into space. But the green grid is what happens if you that's like the plane of the sun, right? That's sort of thinking about this from a solar system perspective. And these are offset by about 23.5 degrees, which is the rotation of the Earth. And the ecliptic's main horizontal meridian here is also, is known as the ecliptic. And you can see it's just the circumference of this giant green celestial circle here. It's a little bit easier to see this if I turn off the local equator and the local celestial grid. And if I turn off the ecliptic here, and if we just focus on the sun, and we watch time advance throughout the course of a year, you can kind of visualize as if we're advancing at several days a second here. So you're just watching the Earth and the planets go around the sun. And that's a little bit easy to see because we've got this green grid behind it that kind of represents that sort of represents the sun's frame of reference. I'm going to put back on the ecliptic here. And you can see that the sun is moving around here. This visualization is actually pretty important for, now I'm going backwards. It's pretty important for the ancients because you can see that from where we are in the Earth, it kind of looks like that the sun traverses over a variety of constellations throughout the year. Specifically, it traverses over 12 of them, and those are known as the Zodiac. And in fact, we can display some of those here as well. If we display the Zodiac Constellations, you can see that sort of the path that the sun makes as we go around it is it travels the zodiacs. Here's Taurus and Gemini and Cancer and Leo and Libra and Scorpio, et cetera, et cetera. And that is us going around the sun. So I'm going to turn back on a couple more grids so we can see some other interesting effects here. So let me go back to now. And let me turn off the constellations again. Set us back to midnight. Okay, cool. Right, so we've been going back on. I'm going to turn back on the horizon here. And now I kind of want to show you what happens when... So this line here is the... right, we've turned the horizon back on, except without the ground, so you can actually see the sun. So one thing we can do is we just sort of watched us go around the sun a bunch as it's going on the ecliptic, but now we're actually going to plot the position of that every single day. So here we're at noon on the vernal equinox, and we're just going to advance day by day and watch the position of the sun where it is at the same time every day. And if you trace out the path that the sun makes at the same time every day, you get this shape that's drawn through the sky. That shape is known as the Analemma. And you may have seen this before on old globes or sort of in other star astronomy related things. And you can see it's sort of made by watching where the sun is at any given time in the sky. So this has two components to it. First of all, this up-down component. And if you take a look at the sort of the green sphere grid behind there, you can kind of see that the up-down component is related to the tilt of the Earth as we're going around the sun. So relative to the horizon, which is the thin gray line in the middle, it goes 23 degrees above that and 23 degrees below that when you're standing on the North Pole. That spread is the difference between the height of the sun at the peak of summer and the height of the sun at the dead of winter. It's just a little bit easier to see here from from the North Pole when you're sitting on top of the world. Everything's a little bit less twisted. And the last part about this is about why there's like this like left-right, why it's like not a perfect line straight up and down. There's this kind of like left-right axis. There's like the width of these two little lobes here. And the width of those lobes come from two surprisingly subtle effects that hopefully I'll be able to demonstrate a little bit better here. One way I'm going to demonstrate that effect is by looking pretty hard at a particular day. So let me turn off this track again. Let me move to November 3rd of, doesn't really matter, but say this year. Nope, that's not it. 2018. Oh dear. Cool. So, right. So here's, let me turn also, I'm going to turn off the ecliptic. I'm going to turn back on sort of our like local celestial grid here. And let's take a look at the sun. So I'm going to zoom in a little bit so we can be very precise about this. So here you can actually see the disk of the sun now. I'm also going to give it a track as well. Basically, we're going to watch the sun's motion over the course of exactly one day. So I'm going to advance this by 24 hours. Here we go. And back. So this is zoomed in the distance on November 4th. The sun traveled in 24 hours. This discrepancy here is not like a glitch or some rounding error of the program. That's real. That up-down motion represents the difference in like, right? Because like we needed to traverse from top to bottom of the thing anyway. So that sort of represents the change in tilt and axis over the sun over the course of a day. But you'll see, like as expected, it came right back to the same like left-right spot. Left-right in star terms is called right ascension. So it came back to the same right ascension as it did before, which was kind of as expected. One other, I'm going to pick a different time of the year and do that exact same demo again. So let's change this instead to September 1st. Find the sun. And here you can see the sun is aligned with this like gray meridian bar. Same thing again. I'm going to turn on the path and I'm going to advance at 24 hours. And here we go. Right. So this is a little bit different. The sun went a little bit further past than where it was before. And how much further past? Well, the answer is about 20 seconds. There. So I just set it back 20 seconds. You can see it's more aligned. Once again, that's not a rounding error. That is a real effect. And the reason why that happened has to do with the eccentricity of the Earth, or the fact that the Earth does not trace a perfect circle around the sun. When the Earth is very close to the sun, it goes very fast around the sun. And when the Earth is far away from the sun, it goes a little bit slower around the sun. And as we talked about earlier, about the sidereal day, the way that we have determined what 86,400 seconds should mean is the average amount of time, the average speed at which the Earth is going around the sun. So if the Earth is going really fast around the sun, it has like a little bit less to catch up for because of that, because of the extra distance between here and and putting the sun back in the same spot. And that little 20-second difference that you saw there adds up. That's 20 seconds per day. And that has sort of an effect because it's sort of an oval that stacks up in one direction for a little bit and stacks up in the other direction a little bit. And it actually sums up to be about 12 minutes, 10 to 14 minutes of time that accumulates between what the sun believes is noon and what our clocks say is noon. because the amount of time that it takes the sun to get back to the exact same spot, which is called an apparent solar day, is many days not the exact same as 86,400 seconds, which we have deemed the mean solar day or average solar day. So that is like one part of the left-right axis. There's one more, and so this part here is called the eccentricity component of the left-right axis, which is also known as the equation of time, which I'll show in a second. But the other component has to do with the just sort of the very nature of the shape of the of the sun. So if I let's do this not by here. So if I trace the path of the sun over the course of a year by hour, yeah. So let me zoom out a little bit. Yeah, so here we go. We're just like, basically you can imagine the sun like coiling itself around the Earth here. And when we get to the like solstices, it like slows down and starts to go the other direction. You can kind of imagine, one way to sort of think about this is the kind of gap. The sun doesn't necessarily, if you had like a string and you wrapped it around a can, right? If your string was the exact circumference of the can, it has to be like perfectly around the circumference. If you tried to like wrap it around at an angle, you would get a different length string. And that's kind of exactly what's happening here. The wider the gaps are between these two like passes, it just needs to go a slightly bigger distance to get back to where it was. It's not a huge effect. It's on the order of a couple seconds every day, but once again, it's cumulative, so it adds up. And the mean solar day is kind of the average of all of this. So in the springtime, like it's got a little bit of a wider coil, so it happens a little bit slower, and at the solstices, it's like a narrower coil, so it happens a little bit faster. And this is known as the obliquity of the ecliptic. And the way to sort of visualize, the classic way to visualize this is known as the equation of time. And it has two different components that are part of it here. So both of these effects stack on top of each other equivalently. So this is the eccentricity thing. Those peaks is just where the Earth is closer and further away from the sun. And here's that seasonal variation because of this like coiling effect that I was just demonstrating here. And when you sum these two sine waves, you get this shape here. And that shape is known as the equation of time. And when you compress that shape onto the sky, and you add in the up-down component of sort of the general inclination of the Earth, you get this shape, which is the analemma that we saw there. Those are some pretty obscure effects, needless to say. And you can see it's not quite symmetrical, and it's sort of these. The reason why it's not symmetrical is because, well, nobody like the solar system didn't like set the ovalness of our orbit to our convenience, so it just is a little squished like this. But this left-right component here, and this is in minutes, so this is anywhere from like minus 15 to plus 15 minutes, so there's about a half an hour variation here. That's why the sun does not rise and set, even if you're like correcting for time zones and everything like that, at exactly 6 o'clock every day. That's why the sunrise and sunsets, like you don't have the longest day on the summer solstice, and you don't have the shortest day on the winter solstice. Because sunrise and sunsets are determined, like 6 o'clock and noon are determined by these like SI seconds and sort of the averages of all of this. But the actual sunrises and sunsets are influenced by some of these other positions as well. Yeah, and that all stacks up to give you this like fairly famous shape that you see, well, Wikipedia, that you see kind of all over the place, from like ancient globes to other things like that too. This is actually very important. This has been known for a long time, since antiquity. One of the main reasons is because if you don't have software like this, you can simulate these effects by simply poking a hole in something that's fixed and like plotting where it shows up on the ground. Or having a mountaintop that you're very familiar with and watching where the sun is, where the shadows cast relative to that. So since antiquity, people have seen these subtle like seasonal effects and were able to calibrate themselves accordingly. Yeah, so those are the major components that go into this like idea of a day. Where's the sort of the eccentricity of the orbits, the fact that we are also going around the sun, and sort of the subtleties of the geometry of watching the sun go up and down because of our inclination to it, all add up to make these subtle changes to the day. There actually are a couple other additional forces at play here that are even more subtle than this. These show up yearly. These have been known to the ancients. Some other ones that's kind of comes up in like the software world is that because of the position of the Earth and the Moon and everything like that, the Earth no longer takes exactly 86,400 SI seconds to turn 361 point something degrees. The Earth itself has been slowing down very, 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 very slowly, like it's only a couple milliseconds slower than it used to be, but that adds up. And every few years, it means that the rotation of the stars doesn't line up with our clocks by about a second, and those are known as leap seconds. And we actually have systems now that the stars are in fact such a good indicator of where we are in the sky. And by stars, I mean really distant ones like active galactic nuclei in the very far reaches of the universe that we can detect with absurd precision. We know such things nowadays that the ancients did not as accurately. Those don't come up as frequently unless you're looking at edge cases in a time library, but the shape of the analemma and the effects of those two features definitely come up every day. You want to know what time the sun rises and sets and where you are in the world. So yeah, that is a lot of information about a day in a nutshell. Are there any questions? I came to know this mostly because I'm kind of an astronomy geek, and I got this sweet piece of software. I was playing around with it for a long time, and a couple of rabbit holes later, and here we are. You certainly can do that. It's hard to do that experiment. Yes, doing that experiment, like punching the hole and seeing the shadow, is fairly easy to do. And the biggest issue is like making sure that it's a little bit tougher at higher latitudes because the shadows it casts are very long, especially in the winter. Plus, in San Francisco, it would not work at all in the summer because you would never see the sun. And it also needs to be a pretty static like piece. It actually works better when you have large monumental landmarks or huge stone pillars placed in strategic places in a circle, for example. Yeah. Cool, thank you.